Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ridwan Shakir bin Muhammad Amzani. My matrix number is CE1900185. So, I will explain for my part for part 2.1. So, this is the diagram for question part 2.1. This is from MATLAB, the simulation. So now I will get straight to it. So we have a VA, transfer function, load, scope here, bus generator, and EMF constant. So for the VA, we set the value of VA is 10, and then we set value for the pulse generator is 1, and then we set value for EMF constant is 4. So and then we just make a connection to it with transformation, load to pulse generator, and then EMF constant. So I think that's all from me. Thank you. Assalamualaikum.
Hello, Assalamualaikum. My name is Syamil Bakri bin Ibrahim. My matric card is CE190170. So today I would like to explain about this lab 2 for control system. My part is 2.2. So now I'm going to explain for my part. So firstly, the scope result print screen of our experiment using pulse generator to generate TD with the desired amplitude for 10 seconds, 40% pulse width, and a phase delay of 3 seconds. Okay, this is the block parameters for pulse generator. So we need to double click on pulse generator on simulation on our Simulink. As you can see here, this one we need to double click here. Okay, for the pulse generator, and it appears like this one for the value for the pulse generator. As you can see here, we can see amplitude 0.4, periods 10 seconds, pulse width is 40%, period, and phase delay is 3 seconds. Okay, so a pulse generator is used to generate TD with the following setting: amplitude 0.4, period 10 seconds, pulse width percentage of period 40%, and phase delay 3 seconds. As you can see, this is the value that when we double click on pulse generator on block diagram. So next is the block diagram used in MATLAB as shown as below. So this is the block diagram that I take from part 1. This is going to continue for the part 2. So yeah, as you can see here, this is the block diagram that I do already before on the Simulink. Okay, I put in on report. Okay, the output scope after the simulation as shown as below. So here I'm going to explain about the output scope. So as you can see, we have analysis period in the scope. We have 3, 0 until 3 seconds, 3 seconds until 7 seconds, 7 seconds until 10 seconds. Okay. So yeah. Okay, so I'm going to take from cursor 1. This is 0 second until 3 second. 3 second here. Okay, this is the 0 until 3 second for the first period. So the second one is 3 second until 7 second. So I'm going to take this cursor 2 until 7 second. And the first cursor is 3 second until 7 second. So the last one is 7 second until 10 second. So the cursor one is here 7 second until 10 second. Okay, that's all. Okay, this is the output scope. We have the no output scope is like analysis period in the scope. So we have 3: before disturbance, with disturbance, and when the disturbance is removed. So steady state error, we have 10 minus 1.25 equal 8.75. For the second one, 10 minus 2.25 equals 7.75, and the third one, 10 minus 1.25 equal 8.75. Okay, so the comment for these three performance analysis is first one, before disturbance, it has larger steady state error. The second one, it has smaller steady state error for with disturbance, and when the disturbance is removed, it has larger steady state error. Okay, so that's all from my part. Thank you.
Assalamualaikum and hi. My name is Nur Aini Nadira binti Kamara Arifin and my metric number is CE190049. So for this lab 2 part 2, I will show the simulation and the output for question 2.3. So as you can see, this is the block diagram for question 2.3. And the constant value is that we put 10, the gain is 8, this is the sum plus minus, and the transfer function we put 0.1 over 0.5s plus 2, and load is 1 over 0.02s plus 0.2, and the gain value for KB is 4, and the pulse generator and the scope. So for the output, we click run. And this is the output for the block diagram. So for the analysis period in the scope here, before disturbance is that from 0 to 3 seconds, 0 to 3 seconds, here we get 1.2% for the overshoot value, and it reached steady state error, and there is a minimum overshoot, which is this is the overshoot. And next is for the 3 until 7 seconds. That we get 3.64% for the overshoot percentage. Here, this. And then the steady state error here is -1, and the overshoot is higher as there is a disturbance. This is with disturbance. And last is when the disturbance is removed, which is here, 7 until 10 seconds. And there is no overshoot since there it is going down like this. And for the steady state error, it's 0 here. And for the comments for this, when the disturbance is removed, is reach steady state error, and there is no overshoot in this part as it only undergoes overshoot like this. So I think that's all from me. Thank you.
Hi, my name is Chong Xin Ling, matrix number CE190008. So for this lab number 2, I'm going to explain part 2, 2.4, show the step to determine a suitable KFF and their respective result in a table. So now let us see. So as you can see here, this is the block diagram without disturbance. So the value here, the input value and the gain and the transfer function, even the pulse generator value there is already explained from my group member. So now I'm just showing the output from this block diagram without disturbance. So now I will run. So this is the scope result there, and this is the waveform that we get from this for the block diagram without disturbance. So I'm going to, so that's it from this part. So I'm going to explain. Another part is regarding on how we get the result, the suitable value for KFF. So we use the same dot diagram as previously, but we add the KFF here after the input. So first of all, we will set the KFF value as 1, and then we will look at the output. We will look at the output. So I'm going to close this first. So first of all, we will set the KFF value as 1, and then to the response graph that we get, we will calculate the steady state error. The steady state error already we get from the previous graph, which is 1.25. And then after that, we change the KFF value, increasing and decreasing randomly, and we will observe the steady state error for each KFF. So now I will change it to our desired, not desired, I will calculate, I'll get the value from our calculation, which is 8. So now let us run and see the output. We calculate by the way, we calculate the KFF value using this formula. KFF is equal to new desired value over steady state error without disturbance, which is 10 over 1.25. We will get 8. So this I'm already change the KFF value as 8. So now let's see. Okay, this is the state no, the output, the scope result. Okay, so we will see that there is the difference. There is the difference from the graph previously. So we can see that there is the, so this is the scope result for the KFF 8. So we can observe that the scope result to find the overshoot. So here we can see that the ruler here, we can get there is already put it here, and we see that the overshoot value is 2.136 for the overshoot value. Then do again the calculation for the overshoot. So the overshoot calculation formula is C max minus C final over C final, and then times with 100, then we will get 1.2. Then from the graph, on the graph scope graph here, we get the overshoot value is 2.136. Then we will minus it from the graph value minus the calculation value, we will get 0.936. And then for the steady state, we will get 10 minus 10, we will get 0. Then the ready steady state from the graph is 0. So for this lab, we can, for this part, feed forward gain part, we can know that the feed forward gain is added in the system because it will help to eliminate the steady state error that been occur in the previous 2.2 graph or in 2.3. So we can conclude that the graph that I have shown just now, you can say that this scope result graph already reached its steady state. So with the help of the feed forward gain. So that's all for my explanation for this part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Khairul Ikhwan Bihamdan. My numeric CE190216. I will continue for my parts. This video is 2.5. Discuss and compare all results above with the expected effects. Using VA equal to 10 volt KB4 and a pulse generator generate TD with 0.4 amplitude for 10 seconds, 40% pulse width, and a pace delay of 3 seconds starting at 2.2. The result indicate a substantial steady state in inaccuracy of 0.85 at 0 minus 3 seconds, which is before the disturbance. The steady state error was likely reduced between 3 seconds and 7 seconds in the system with disturbance. With a value of 7.75, the steady state error was increased to its initial value of 8.75 after the disturbance was removed from the system after a period of 7 seconds to 10 seconds. To remove the steady state error that occurred in 2.2, you can see in 2.2, a feed forward gain KFF was added to the system in 2.3. We utilize it as the KFF in this station of the experiment. As a result, we can see that when the system is not disturbed by the pulse generator, there is no steady state error. When there is a disturbance in the system, the steady state error is -1. We can argue that feed-forward gain in the system help the graph attain its steady state. Thank you.